Hello, today we will be going through the J277 specification for OCR GCSE Computer Science. The paper is split into two sections, Section A and Section B. In Section A, you will be asked questions in Natural English, OCR exam reference language, and flowcharts. You will respond or be expected to respond in pseudocode, flowcharts, bullet points, exam reference language, or a high-level programming language such as Python and Natural English. Section B is testing your ability to design, write, test, and refine programs. So if you are asked a design question in Natural English, you may be required to use pseudocode, flowchart, tick box responses, and Natural English. If you are asked a write question using pseudocode, Natural English, or flowchart, you may be responded in exam reference language or a high-level programming language such as Python. Test questioned asking OCR exam reference language, you may respond using trace tables, creating test plans, identifying suitable test data, and then a refined question, also asked in OCR exam reference language. You can respond in the OCR exam reference language, a high-level programming language such as Python, or Natural English. It's very, very important to read the question carefully to understand what it is that you've been asked to do, as some questions may specify that your response may need to be in a high-level programming language or OCR exam reference language, and other questions may allow you to write an algorithm using Natural English or pseudocode, etc. So please read the question carefully to understand what exactly you have to do. Here are some command words that you may see in the exam. And it's really important to kind of understand what the question is asking based on the command words, and also have a look at the mark allocation, because that will give you a rough idea of how much you're supposed to be writing or how much you should be elaborating on your answers. So here are the assessment objectives. You've got AO1, which demonstrates your knowledge and understanding of the key concepts and principles of computer science. You've got AO2, which apply knowledge and understanding of key concepts and principles of computer science. And then AO3, analyze problems in computational terms to make reasoned judgment, to design, program, evaluate, and refine solutions. So in paper 1, you can expect 21% of the paper being AO1, 29% being AO2, and 0% AO3. And then for paper 2, you can expect 9% AO1 question, 11% AO2, and 30% AO3. And then you can see the breakdown at the bottom. So AO1 is 30% of your questions, AO2 is 40%, and then AO3 is 30%. So today we're going to talk about paper 2 element, and I will try and do a separate video for paper 1. So 2.1.1, computational thinking. So the main things you need to know about this in this part of this topic is abstraction, decomposition, and algorithmic thinking. Or sometimes you may hear logical thinking or computational thinking. So abstraction means focusing on important details while ignoring unnecessary ones. It's like zooming in on what matters the most. A key example that we've used a lot is the London Underground tube map, or the TfL tube map, and that often tells you just the routes and the station. We get rid of any unnecessary details such as road names, landmarks, etc. that you may not need to know. Decomposition is breaking down a problem or big problem into smaller manageable parts. It's like solving a puzzle by looking at each piece. And then you have algorithmic thinking. It's about coming up with step-by-step instructions to solve a problem, just like following the recipe to make a cake. 2.1.2, designing and refining algorithms, creating and refining algorithms. You've got input, it's information or data needed to start solving a problem. Processes, steps or actions we take to work with the input. Output, results or answers we get after following the processes. You shouldn't be able to know what a structure diagram looks like. Diagrams that show how things are connected or organized, like a map for understanding a problem. So on the right, you can see an example over here of a structure diagram. So you've got a sat nav and you've got an input destination, and you see new destination or saved destination. And if you've got output direction, we can see a map or a list view. You've got pseudocode, writing out instructions in a simple way, almost like writing a story with text. With pseudocode, it's very important that you write your pseudocode in a logical, sequential way that makes sense. We've got flow chart using shapes and arrows to show the flow of steps in a process. As you can see at the bottom, we've got a line. They generally tend to be going in one direction. You've got a process, which is a rectangle. You've got a rectangle within a rectangle, which is a subprogram. It's often a separate flowchart and called upon in the main flowchart, kind of like how we use functions within Python programming. You've got input-output, which is the parallelogram there, and then you've got decision. Now, decision is the only shape within the flowchart that will have two lines going in and out, or two lines going out of it, sorry, a yes and a no line. Okay, and they're normally representative of an if statement within a program. And then you have the kind of oval shape there, which is the terminal, and that's normally the start and end of your program. Common errors are mistakes that can happen while writing or following instructions, and trait tables are used to keep track of how data or instructions change step by step. So we've got a rough program here. It shows you step by step of what's happening. So we start counting from 1, and then while the num is less than or equal to 5, we keep counting, check if the num is even, if it's divisible by 2. We're using mod here. We've got print, we're printing a number, and then we're iterating. So this shows you what's happening step by step. 2.1.3, searching and sorting algorithm. We've got binary search, finding an item in a list by repeatedly dividing the list in half. You may be asked to show the steps or paths within a list, a pre-given list. Now remember, binary search can only be done if the list is sorted. Linear search can also be done on an unsorted list, and that's checking each item in a list until finding the desired outcome. Those are the only two searches that you need to know. And then the sorts that you need to know are bubble sort, insertion sort, and merge sort. So bubble sort is arranging items in a list by repeatedly swapping out adjacent elements that are in the wrong order. So what happens with bubble sort is you have your first element, it gets checked with the first one or the second element, and if it's in the right order, then they move on to the next element, and we keep comparing two pairs until we get to a sorted list, and we keep swapping one element at a time. For insertion sort, it builds a final sorted array one element at a time by inserting each unsorted element into its correct position within the sorted part of the array. And then you've got merge sort, it splits the list into smaller lists all the way until we get into independent element, and then it sorts them back out, merging them back together. Then we have programming fundamentals for 2.1. Variables are containers used to store data like numbers or words that can change during the program. We often have local variables and global variables. Global variables are predefined at the top of the program and can be used in multiple functions and in the main program, whereas local variables would only be used within that main function. We have constant values that stay the same throughout the program. For instance, if I have the value of DAT or pi within a program, it's not going to change while the program is running. We have operators, symbols used to perform operations on variables or values. So at the bottom right, you can see over here, we've got comparison operators. We've got two equal signs here is equal to, not equal to, so the exclamation mark there is not equal to, got less than or equal to, greater than or equal to. And then we also have the arithmetic operators for addition, subtraction, multiplication, division, modulo, which tells you whether there's a remainder or not, and then quotient. Okay. What's important here to realize the difference between assignment and casting. If we say in Python, for instance, if we're using double equals, we're comparing things on either side of the equal sign. If we use one equal, we're telling Python this is what it's equal to. Then we're looking, and sorry, just the arithmetic operation, I forgot exponentiation. So it's basically to the power of. Input and output, ways for the program to interact with users or other parts of the computer. Input, as we've mentioned in the previous slide, is data entered into the program. Output is the data displayed or produced by the program, showing a result on the screen. We've got assignment, setting a value to a variable using the assignment operator, just the one equal. We have a sequence, writing instructions in a specific order for the computer to execute one after another. We've got selection, making decisions in a program based on conditions using if, elif, else statements. Iterations are loops. When we think about loops, we have two different types of loops. If you're having a count controlled loop, that means you know how many times the program is going to run or loop. That would be a for loop. If we have a condition controlled, so it keeps looping until the condition is met, it's using a while loop. Then we have data types in 2.2.2, and that defines the type of data that can be stored and manipulated in a computer program. So some of the common ones, integer, used for storing whole numbers without any decimal point. You have float or real, which include numbers with decimal point. We've got Boolean, which is values like true or false, yes or no. We've got character, which represents a single letter, digit, or symbol. We've got strings, which represents a sequence of characters, words, or sentences. Casting or type conversion is the process of changing a variable from one data type to another. For instance, when we have integers, we may then cast it to a string to be able to print it. Additional programming techniques. String manipulation involves working with sequences of characters or strings to modify, combine, or extract information. Concatenation is combining two strings together. Hello plus world would give us hello world with no gaps in the middle. Length, finding the length of a string is len hello. So that would tell us how many characters we have in that string or what the length of it is. And then slicing is extracting a specific portion of a string called a substring. Now we might want to slice a string, for instance, when we're setting username, whereby we might say the first letter of the first name and 5 letters of the surname, etc. Then we have file handling operations. They are actions performed on files stored on a computer. We've got open, read, write, and close. So starting to use a file, we need to open it, read, getting information from a file, write, putting information into a file, and then close, finishing with a file. We've got records, which is a way to store related pieces of information, fields, together under one name, which is a record. And they're often used in databases. Storing details of a person, name, age, address as a single record. The more people you have, the more records you'd have because each individual would have their own record within that database. Then we have SQL, which is structured query language, a language used to communicate with databases to retrieve or manipulate data. For example, using SQL to find all customers with a specific age range in a database. We would do selects from and where, that's what we would use. So for instance, if I did want to find all customers within a specific age range within a database, I could say select all customers from TBL customers to table customers where age equals less than 50. Arrays, collection of items or elements stored together under a single variable name. Arrays are very similar to lists, and just in Python we use arrays instead of lists. Arrays, so we have 1D, which is a list of items accessed using a single index. So we have normally a number within square brackets, and that's normally the index number there. We have a 2D array, which represents a grid or table of items accessed using two indices, so the row and the column. So for instance, you might have 201 within the square bracket, that would be the two indices. Then we've got subprograms, so sections of code that perform a specific task and can be reused multiple times. We've got functions that return a value after performing a task. We've got procedures which perform a task without returning a value. And then we've got random number generation. Now, often you've used it in simple number guessing games, etc., that you may have programmed. We use the random library in Python, and then we can generate a random number and store it in a variable. We've got defensive design. It's anticipating misuse, thinking about how someone might use a program incorrectly or for the wrong reasons, and taking steps to prevent problems. So we might use authentication, making sure that only authorized users can access certain parts of a program or system. That's where we use user access levels. We have input validation, checking the data entered into the program to ensure it meets certain criteria, valid format, within expected range, and sometimes just checking that there's no blanks before processing it. We've got maintainability, use of subprograms, breaking down a program into smaller sections that perform specific tasks, making it easier to understand and modify. We've got naming conventions, using consistent and meaningful names for variables, function, and other elements in a program. It makes it easier for somebody, when we use correct maintainability, it's really easy for somebody to open the code and understand what's happening. Subprograms can be used in multiple different programs, so it's more efficient than the programmer writing the entire program out again and again. Indentation, using spaces or tabs to organize code visually, making it easier to read and understand. And then we've got commenting. Obviously, in Python, we use hashtag or the speech mark or single apostrophe that would help us make a comment, and they're often green within the code to explain the purpose of how it works, helping others understand the code later, and it's discovered during testing. Then that moves us nicely onto testing. It's checking a program to find errors or problems, and it ensures it works correctly. We have iterative testing, which is done repeatedly using the development process to catch issues early and make improvements. Final or terminal testing done at the end of the development process to ensure the program is ready for use. We've got syntax errors, is mistakes in the structure or grammar of the code that prevent it from running. It might be a missing speech mark or missing bracket or something spelled incorrectly. And then we've got logic errors, which is flaws in the program's logic. They cause incorrect behavior or result. So it might be that you've called the wrong variable, etc. Test data, we've got normal data that's normally expected to be accepted by the program. Boundary data, so if I say it needs to be between 0 and 10, boundary would be 0 and 10 to make sure that those are accepted. Invalid data, if I say between 0 and 10 and I put in a letter, that would be invalid. Erroneous, it's intentionally designed to cause errors, helping identify weaknesses. So erroneous data, I might put an exclamation mark. And then refining algorithms is making improvement to the logic or steps of an algorithm to optimize performance, fix issues discovered during testing. We've got Boolean logic. The logic diagrams here are visual representations of how logic operations like and, or, and not work using symbols. And a logic gate that output true only if both output inputs are true, and if both inputs are false, it will output false. Or a logic gate that outputs true if at least one input is true, and not a logic gate that outputs the opposite of its input. So if not is inputted, if we're using a not logic gate and truth is inputted, then false would be output, and vice versa. We've got truth tables. They show the possible combinations of input. And you can see an example here and show what the output would be for that. Combining operators using multiple logical operations together to create complex conditions. Example A and B or not C would basically be logic gates, multiple logic gates used in one circuit. We've got problem solving, using truth tables to analyze and solve problems involving logical conditions. Example, determining under what conditions a certain statement or condition is true. We've got and here, which looks like a D shape. We've got an or, which almost looks like a bit of a rocket. And then we've got a triangle for negation or not, with a little circle there. Just important to also realize that not has one input, whereas and or have two. Truth tables, so I briefly mentioned about this before. We've got P and Q, logical connectives, and or not. So it basically would only output true if both P and Q were true. Okay, and then we've got or if either, so either P or Q are true, then it outputs true. If both are, it also outputs true. Okay, and requires both statements to be true or requires at least one statement to be true. Then we've got 2.5.1, which is languages. We've got high-level programming languages that are closer to human languages and easier to understand. We've obviously used Python. You could use JavaScript and Java for these as well. We've got low-level languages, programming languages that are closer to machine code, understood by computers, less human-friendly, but more efficient. They provide direct control over hardware and system resources, things like assembly language and machine code. Translators, software that programs that convert code written in one programming language to another form that the computer can then execute. It enables programmers to write code in high-level languages and translates it to machine-readable format, things like compilers and interpreters. Compile convert entire programs written in high-level languages like C or C++ into machine code before execution. It produces executable files that can run independently, so they don't actually need the IDE anymore. Interpreters execute line by line, so execute code line by line, translating and running each instruction on the fly. It does not produce a separate executable file, and it requires the interpreter to be present to run the code. Examples are like Python, and this is where the code will run and it will pause at where the error is. The integrated development environment or IDE, we have editors, text editors with features such as syntax highlighting, auto completion, code formatting for writing and editing code. We've got error diagnostics, so tools that identify and highlight syntax errors, logical errors, or warnings in the code. We've got runtime environment provided by the IDE to run and test code, including simulation of program execution. We also have translators, built-in compilers or interpreters that allow programmers to write, execute, and debug code within the IDE. Got a bit of a cheat sheet here to show you what it looks like in Python. So you can see here assigning variables and data types. We've got basic syntax of printing. This is what comments look like. For loop looks like this. A while loop looks like that. We've got conditional if statements look like this. We've got each of our arithmetic operations, what they look like. String operations, the John plus space plus dough would equal John Doe with a space in the middle. Repeat hello equals hello times 3. It would say hello, hello, hello. And then we've got user input. So we're asking the user to enter your name as a string. We're asking the user to enter their age as an integer, which is a whole number. We've got list. This is what lists look like. And then accessing list elements. So appending, we add it to the list. Removing, we remove it from the list. And then we print what the list shows. And we have indexes in square brackets here. Functions look like this. They start with def, the name of the define. We've got the name of the function, and then any parameters are in brackets, and we return whatever parameters we'd like to use in the main program. We've got dictionaries that look like this. Writing or file input and output, writing to a file. So we'd open example.txt, write as file, write hello world. And then we've got reading from a file, we open it in R mode. And then we've got error handling to try to enter, you enter this number until that's not a valid number. Then we've got a summary of key concepts here, data type, integer, float, string, and boolean. We've got your arithmetic operators, your comparison operators, and then our logical and, or, and not. We've got control structure. These should be uppercase. Conditional statements, if, elif, and else. Loops are for and while. Define a function using def. Call a function by its name and pass the required argument called parameters. We've got lists, ordered, mutable collections of elements. We've got dictionary that are unordered collections of key value pairs. We've got file operation. So we use open with mode read and write, and append, which is adding to a file. And use with statement for safe and concise file handling. Error handling, use try and except blocks to handle exception. You can see here just a bit of an overview on what we've already covered directly from OCR. We've got iteration, while loop, do until. That doesn't work in Python, but you can still use that when you're trying to talk about, say, for instance, in the pseudocode, etc. We've got if, then else, and then case select or switch. got string handling operation, file handling, and arrays, so just ideas or examples of what that could look like. We've got what procedures look like, calling a procedure, a function, calling a function, and then random numbers. And that is the end of paper 2. I hope you found this helpful.